Hey ChemStars, this is Mrs. Vanderlei bringing you the next edition of ChemStar video. This is 9.3 number 1. So what are we going to do first? So we're going to learn how to compute theoretical yield, actual yield, and percent yield. So before you do that, you do need your periodic table and your calculator. So why don't you get it out now? Pause, and then when you're done, come back. All right, welcome back. Hopefully you got everything you need. So what is percent yield? It's the actual yield from lab divided by a theoretical yield from stoichiometry times 100%. All right, so if you actually make a 1.0 grams of silver in the above example, what's your percent yield? All right, well, percent yield is equal to, all right, actual over theoretical times 100%. All right, so here I have 1 gram divided by, oh, well, how much should I make in my above example? All right, well, let's go back. I'm on the previous page, and this is where we took the copper, the silver nitrate, and we made pure silver and copper nitrate. And we started out with grams of copper, and we found moles. And then I used the BCA table, and then I ended up making 30.7 grams of silver. And I was going to try to retire off of that, remember? And I was only going to make $12.59. I'm not going to retire on that, but this is what I should make. All right, this is my theoretical yield. All right, let's go back to the next page. So now here is my theoretical yield, and I'm going to multiply it by 100. Now notice something. All right, my grams cancels out, so I have no units except for the percent sign. So go ahead and get out your calculators and calculate the percent yield. Don't forget to multiply it by 100%. All right, I got 3.26% yield. That's pretty bad, isn't it? So you may be wondering, where'd my other 20.9 gram or 29.7 grams go? Well, if it's not in my pocket, no, I'm not dishonest. It may be down the drain. Maybe when you filtered it, you lost some, all right? You have a poor percent yield, don't you? And so it says if your percent yield is less than 100%, then you've lost some of the product. Let me tell you a quick story. My roommate at Purdue was a chemical engineer. I was a chemistry major. She was a chemie. When she graduated, she got a job at Morton Salt up in Chicago. And her job was to try to find where in their process to make Morton Salt they were losing some of their product. Their percent yield was too low. So her job was to look at the process and determine how can this be more efficient to make the percent yield higher. Why would Morton Salt even care? Well, if you lose product, you're losing money. All right, so she was trying to make the whole process more efficient so that the Morton Salt wasn't losing so much money. All right, so this is really important in industry. They care about this, all right? So if you are responsible for extracting the silver and you only get a 3% yield, you may be looking for a new job, all right? So what if your percent yield is greater than 100%? You do not have a pure product. There must be something else to cause your mass to be too big. Well, the most common percent yield greater than 100% would be it was wet. A lot of these processes occur in a water solution, an aqueous solution. And if it is not dried enough, then you're going to have a percent yield greater than 100%. I'm not saying that's the most, the only way, it's just the most common way. There is something else like water mixed in your product, all right? So letter E is, again, the law of conservation of matter. You cannot create matter. That's why you really can't have greater than 100%, or it's not pure. And you can't destroy matter. And therefore, it's someplace you just lost it, all right? It could be down the drain. It's there. You made it, but you didn't collect it, all right? All right, so now we're going to talk about limiting reactants and percent yield, okay? It says use the following procedure when you're given quantities of all reactants. Up until now, you're always given just one. Remember, if you go back and you look, you always had something in excess. You had excess oxygen. You had excess silver nitrate. All right, what happens if nothing is in excess? You have a finite quantity of all your reactants. What do? Well, I'm going to tell you. You take your limiting reactant. Well, it's the reactant that's used up first, and it determines the amount of product. The excess reactant is the reactant that which is left over. So let's go back and look at my brownie example from how I started this whole unit. All right, so what happens here? We go back and look at my Ghirardelli brownie mix, all right? 1 brownie mix and 1.5 cups of water, 0.5 cups of oil, and 3 eggs makes 16 brownies. Sounds yummy, doesn't it? But what if I look at my cabinet and I have 3 brownie mixes? Of course, I have as much water as I want. 4 cups of oil, because I just brought a brand new thing of oil, so there's plenty of oil in there, 4 cups. And I have 6 eggs in the refrigerator. Which ingredient is going to run out first? All right, well, let's do this. I can put a 3 here because that's how much I have. I still have excess water. All right, I have 4 cups of oil and I have 6 eggs. All right, which one's going to run out first? All right, I'm going to look at my brownie mix and I'm going to do what I need to for find the change. So if I bring the 3 down, all right, what's 3 divided by 1? That's 3. Well, I'm going to skip water because I know I have plenty of that. So what is 3 times 1.5? All right, I think that's 1.5, and I have 4 cups, so I'm plenty there. Well, what's 3 times 3? Isn't that 9? Do I have 9 eggs? I got 6 eggs. I don't have enough eggs to use 3 brownie mixes. So let me look at the eggs. Okay, I'm going to do the exact same thing, all right, but this time using the eggs. So what is 6 divided by 3? 2. What's 2 times a half? Isn't it 1? What is 6 divided by 3? 2. What's 2 times 1.5? Isn't that 3? What's 6 divided by 3? 2 times 1. Isn't it 2? Why do I have negative signs? Because these are all my reactants. Remember that? Now let's go ahead and subtract. 3 minus 2 is 1. Excess minus 3 is still excess. 4 minus 1 is 3, and 6 minus 6 is 0. The limiting reactant is that which is used up first. Look at these numbers. That which is used up first is my limiting reactant. I have 0 left when I'm done. What do you notice about the other reactants? They're all a positive number, a positive 1. Excess is positive. I have a positive 3. They're all positive. So if one of these is 0 and the rest of them are positive, you have found your limiting reactant and that which is excess, okay? So which one will run out first? I think we can all agree it is my eggs, right? There's my limiting reactant. All right, so now what? Which is going to be an excess? Oops, hang on. There we go. Well, I think you'll agree it's my brownie mix, oil, and my water, right? These are my excess. And now what? How many brownies can I make? Well, let's go back. Now I'm going to use my limiting reactant, because remember what we said? It's the reactant that's used up first. And did you highlight that? Did you star that? And it determines the amount of product. So I'm going to take my 6. Well, what's 6 divided by 3? 2. What's 2 times 16? I'm going to make 32 brownies. Okay. Let's go on. All right, so I can determine the limiting reactant from the given amount of both reactants and determine the amount of product made. All right, so you determine the limiting reactant in a chemical reaction. You first look at the definition of a limiting reactant. It is used up first and it determines the amount of product. What else did we notice? It is going to be 0, and then the excess has to have a positive number when you're done. All right, so choose the first reactant and see if it works. If not, choose the second reactant. And of course, you might want to use the pencil because you might have to erase, okay? So now what? Let's just start off easy. I just start with moles to make life easy on you. If you have 2 moles of nitrogen and 3 moles of hydrogen, which is the limiting reactant? Okay, so let's do this. I have 2 moles of nitrogen and 3 moles of hydrogen. Of course, I have 0 moles of ammonia. Why? Because it's my product, okay? So what am I going to choose first? Choose your first reactant, all right? So here we go. Well, what's 2 divided by 1? 2. What's 2 times 3? 6. All right, I got a 0 here. And now what? I got a -3. This is Indiana Jones and the Last Crusade. You might remember this scene. And what does the old knight say? He chose poorly. So what happens here when we have a 0 and a -3? You chose poorly, all right? Did you find the limiting reactant? No, why not? Because you cannot have a negative amount of reactant when you're done. So let's get rid of these, all right? Okay, they're gone. So let's start again. Now what? Choose the first reactant and see if it works. If not, choose the second. All right, I'm gonna use hydrogen, right? So what's 3 divided by 3? 1. What's 1 times 1? 1. All right, let's check this out. So, I have a 0 here and a +1, right? Now what? Did I choose wisely now? Yes, I did. All right, I have a 0 and a positive number. So now I'm ready to go ahead and determine how much ammonia I'm going to make. Well, what's 3 divided by 3? 1. What's 1 times 2? 2. So I make 2 moles. It works, okay? So I would actually like to go ahead and go to the next page, okay? So go to the next page for me. All right, I can determine the limiting reactant from the given amounts of both reactants and determine the amount of product made. All right, so if I have, let's see here, 5 atoms of carbon, which I have right here, and 6 molecules of hydrogen, which I have right here, what's the limiting reactant? Okay, let's do this. How much CH4 is actually made? Well, what's the first step in either of these problems? What do you have to do? You have to balance them. So go ahead and balance these for me. I think if you put a 2 here and a 2 here, you're going to be all set. All right, so how is this going to work? Well, what if I use 1 carbon and 2 of these? What do I make? Make 1 of those. Let's do it again. What if I use 1 carbon and then 2 of these? Well, what do I make? Another 1 of these. I'm not done yet. I still have more of everything, right? What if I use 1 carbon and 2 of those? What do I make? I make 1 of these. Well, can I keep going? No, why not? Because my H2s, I used them all up. So what's happened here? Excuse me. I still have these 2 left over, don't I? I have none of these left over, but I still have 2 leftovers. What else did I happen? I made 3 of these. So let's see how that works over here. If I had 5 to start with, 6 and 0, oops, and 0, all right, let's start, well, we know with the hydrogen, right? We already determined that one's going to be used up. Let's see. Well, what's 6 divided by 2? 3. What's 3 times 1? 3. So let's go ahead and subtract. I have a 0. And what else do I have? I have a positive 2, don't I? Look, that 2 are these 2 right here. So this 2 are these 2. Notice I have none of those left over. I wiped them all out. Well, now what do you notice? Well, what's 6 divided by 2? 3. How many did I make? 3. Isn't that what I did here? Didn't I make these 3 here? I sure did. Okay. I really like that picture, don't you? Let's try the next one. We have 8 atoms of sodium, 3 molecules of O2, which is a limiting reactant. How many moles of sodium? Just be sodium oxide. There shouldn't be an I or a 1 or whatever. That's mis typo right there. Can be made. All right. So what's your first step? Always. You have to balance it. Now notice your 8 and your 3 have nothing to do with the balance. All right. So balance like you did in the last chapter. Okay. So take a few seconds out and do that for me. All right, well, I first put a 4 here and a 2 here. So what do you think? Did you agree with that? I hope so, because that's what I got. All right, now what? Well, kind of do the same thing that I just did earlier. All right, I need 2 sodiums and 1 oxygen. So I need 2 sodiums. All right, come on. There we go. And 1 oxygen. I just need 1 of those. All right. And I get this. Okay. Let's try the next one. I need 2 sodiums and 1 oxygen. All right. And look what I got. You go ahead and finish this off for me. Are you working on it? Okay. This is what I did. I used up 2 more. And now made 1 of these, and then I used up 2 more. Oops, I used 1 of those. And made 1 of those, and made 1 of those. Well, what happens at this point? I'm out of sodiums, aren't I? So even though the 4 is my bigger number, I used them up. All right, I still have some leftover O2s. All right. Well, how many O2s do I still have left over? Those right here. Well, let's see if this shows that, okay? So I start off with 8, I start off with 3, and of course I start out with none, didn't I? All right, well, which one do I know is my limiting? Oh, it's the 8. So what's 8 divided by 4? 2. 2 times 1 is, oops, 2. All right, now what? Well, it was 8 minus 8 is 0. What's 3 minus 2? 1. See what happens. All right, this 0 tells me I used them all up. This 1 tells me I still have 1 molecule left over. And now what? It works. So what's 8 divided by 4? 2. What's 2 times 2? 4. All right, so how many did I make? 4. Does that make sense? Well, how many of these did I make? Oops, I made, come here, 4 of those, didn't I? Sure did. So that represents this. All right, number 3, if you have 7 moles of ethane and you burn it with 10 moles of oxygen, which is a limiting reactant, how many moles of CO2 and H2O can be made? Why don't you do this one all by yourself? And when you are done, come back. All right, so you did. Did you first balance it right? Okay, hopefully you did. Then what? Did you create your BCA table? So you put in your 7 and your 10. So that's where these numbers came in, right? Also you have 0, 0. Well, what happened when you made the C2H6 your limiting reactant? Did you choose wisely or did you choose poorly? All right, my guess is that you chose Hmm, poorly. All right, you'd have had a negative number. This is like a 20 something, 24 something, I forgot what. But anyway, you wouldn't have enough. So you needed to make oxygen your limiting reactant, okay? So 10 divided by 7 is a fraction, I guess 1.45 times 2, you get 2.9. So when you are done, you get a 0 and a positive 4.1. So what does that mean? You can keep going. You found your limiting reactant. It is oxygen. Your excess is 4.1. And now keep going. What is 10 divided by 7 times 4? I got 5.8. 10 divided by 7 times 6 is 8.7. And those are how many moles I can make. So why don't we stop here? And what I'd like you to do now is here is this. So this is page, 7 and 8. So here, draw your pictures. All right, answer questions. Draw your pictures, answer your questions. Notice this is moles and moles. All right, go ahead and do that. And here's moles and moles. All right, so go ahead and work on page 7 and 8, just like what we did on the video, okay? So don't wait to be great. We'll see you next time, and then check your answers when you're done. Bye-bye.